All right, we're going to end this chapter and this unit looking at this whole chapter we've been talking about gases assuming they're ideal. And at certain temperatures and pressures, that is, they get really, really close to that approximation. And that's how 99% of the time, that's how we treat gases. Um, but we're going to look at the conditions where gases aren't ideal and how we deal with that. So let's just kind of review this. What does this ideal mean? Well, an ideal, we basically say that the gas molecules themselves have no volume and little to no attraction with each other. We know that this isn't true. All right, real gases have a volume to them. And what we'll discover later, we'll talk in another unit, is that they are attracted to each other. We call this attraction intermolecular forces. Sounds a little sci-fi, but that's what they're referred to. And we'll go in a little bit more in depth in another unit about what intermolecular forces are and the different types. But as we've assumed in this whole chapter, under normal conditions, real gases are approximately ideal. And what are those conditions? What are those normal conditions? Well, low pressure and high temperatures. And when I say high temperature, we consider like 0 degrees Celsius to be high. And you think about that, like, wait a second, that's the freezing point of water. Well, if you're using the Celsius scale, 0 degrees Celsius seems kind of low. But when it comes to gases, what scale do we use? 0 degrees Celsius is 273 Kelvin. And so we might feel that 0 degrees Celsius, oh, that's cold, that's got to be pretty low. In terms of gas properties, that's still considered high for a gas. So when are gases not ideal? When we have high pressure and or low temperature. Think about why that makes them not ideal. If we increase the pressure on a gas, so let's say we have like a flexible container, and we start to shrink that container down and increase the pressure on the gas, what are we forcing those molecules to do? It's going to be more contact between molecules, which means the gases occupy more volume. And if we decrease the temperature on them, what happens to their movement? So if we go to low temperatures, the gas molecules start to move very slowly. And start to stick to one another. There's more attraction between them. Because if you take a gas and you start to cool it down, what happens to it? Well, the molecules get so close together that then it starts to go into the liquid phase. And so when gases start to get to that low temperature, they're going to be more attracted to each other. And we can still use the ideal gas law in these non-ideal conditions. We just have to modify this a little bit. The ideal gas law, we modify it, it becomes this. We still have pressure here, but then we got this weird term. So that's our pressure term. Our volume term looks like this, and that equals nRT. And what does all of this mean? Well, this little addition here is the correction that gets added for molecular attraction. And then this term is the correction for the volume of the molecule. And those are typically things we'll look up. I'm probably not going to have you do any equations or calculations involving these corrections, but this is just to show you that we do have methods to correct for when these real gases behave non-ideally or they're put into conditions that aren't considered ideal conditions. And we can still use the ideal gas law. There's just a little bit of math that we have to do in order to correct for that.